Hello everyone. So in this tutorial, we're going to have a brief overview of the processes of oxidation and reduction. The reason why this is so critical to understanding reactions in aqueous solution is that oftentimes when we actually observe these types of reactions, what's happening is that electrons are being transferred from one reactant to the other. And so in order to understand what products are formed and understand exactly how, in some cases, even to balance the equations associated with these reactions, then we have to have a clear understanding of when we are losing electrons and when we're gaining electrons within a substance, and that amounts to understanding oxidation and reduction. Just a quick note, it's also frequent to run across these reactions where oxidation and reduction takes place as being referred to as redox reactions. So don't let that alternative terminology fool you. It all amounts to the same type of reaction. So in order for us to understand, and not only understand, but also remember which process represents which gain or loss of electrons, then we have these two mnemonic phrases. These phrases are designed to help us remember exactly what's going on. Basically, Leo says Ger is really all about understanding that the loss of electrons is oxidation. Okay, so Leo. And Leo says Ger because the gain of electrons is reduction. So G-E-R, Ger. Now, sometimes we could also even use this other phrase, oil rig, to sort of remind us as well. All this represents is oxidation is loss of electrons, so O-I-L, oil. And rig represents reduction is gain of electrons, so R-I-G. Right, so it's just a quick way to remind us, okay, if I'm gaining electrons, then that's reduction. If I'm losing electrons, then that's oxidation. The other important thing to keep in mind is that if reduction occurs in a reaction, then oxidation also has to occur. And the opposite is also true. If oxidation occurs in a reaction, then reduction also has to happen within that same reaction. Okay, now, obviously, in terms of sort of studying and understanding these definitions of oxidation and reduction, we can see that it's critical for us to be able to track the number of electrons that are associated with a particular substance so that we can then see the migration of these electrons back and forth during redox processes. And so we have to find a way to track the number of electrons associated with a particular reactant. And so the way that we do that is, if we think back to last year, there is such a system by which we can track the number of electrons assigned to the atoms within a substance, and that's, again, the rules governing oxidation numbers. And so to quickly review these rules related to oxidation numbers, all right, the easiest rule is that if I have an atom in its elemental form, then the oxidation number is 0. So for example, if I have zinc all by itself is an element, it has an oxidation number of 0. It also extends to nonmetals. So if I have chlorine gas, well, chlorine in its diatomic form in the gas state is an element, and so chlorine within diatomic chlorine gas would have an oxidation number of 0. If I have any monoatomic ion, then the charge of the ion is the oxidation number. So for example, if I have sodium cation, well then the oxidation number for sodium and sodium cation is +1 because the charge of the sodium cation is +1. All right, similarly, if I have, say, the sulfide ion has a charge of 2 minus. So that means that the oxidation number for sulfur in the sulfide ion would be -2. From there, all right, there are some rules that govern the oxidation numbers for specific nonmetals. So for oxygen, the oxidation number is almost always -2. The only exception is if I have a peroxide. Now, a peroxide is a substance that actually has oxygen atoms bonded in succession to each other. So if I have a molecule that has this particular arrangement, then that's a peroxide, and each oxygen within the peroxide would have an oxidation number of -1. Okay, now hydrogen, if the hydrogen is bonded to a nonmetal, then its oxidation number is +1. If it's bonded to a metal, then its oxidation number is -1. Fluorine always has an oxidation number of -1 in all cases. All of the other halogens, so basically chlorine, bromine, iodine, they have oxidation numbers of -1 provided that they're involved in a binary compound. So something like sodium bromide. Well, the bromine is part of a binary compound, so it has an oxidation number of -1. Say if I have calcium chloride, each of these two chlorines would still have an oxidation number of -1 because calcium chloride is a binary ionic compound. However, if I have an oxyanion, like something like, say, the perchlorate ion, here the chlorine is not going to have a -1 charge. It's going to have, or a -1 oxidation number, I should say. It's going to have an oxidation number that's positive, and as the number of oxygens changes in the oxyanion, so for example, if I'm looking at the chlorate ion versus the perchlorate ion, then the oxidation number is going to vary for the chlorine, and it will be positive in this case. Now, the last rule has to do with what the sum of the oxidation numbers should equal for a specific species. So if I have a neutral compound, something like carbon dioxide, water, glucose, any neutral compound, the sum of the oxidation numbers should sum up to 0. Okay? Now, if I have a polyatomic ion, like say the ammonium ion, or if I've got something like the bromite ion, for example, then basically the sum of the charges in the polyatomic ion will equal the charge on the polyatomic ion. So that means for the ammonium ion, then all of those oxidation numbers should add up to +1. For the bromide ion, then basically what I should have is a sum of oxidation numbers that should equal -1. Okay, now, again, these rules don't cover every single element in the periodic table, just enough so that basically if I wanted to calculate the oxidation number for elements in a particular compound, I should have enough to get me going where if I do some simple algebra, I'll be able to figure out the oxidation numbers for the other elements involved in the compound. So let's take a couple of examples and apply them specifically to redox reactions. So take, for example, this first reaction right here. I have 2 moles of strontium that are going to react with oxygen, and that's going to give me strontium oxide. So let's actually assign the oxidation numbers. Okay, so if you recall, any element has an oxidation number of 0. So strontium by itself is a metal, it's an element, so its oxidation number is 0. Oxygen, in its diatomic state, and assuming it's a gas, is also an element, so its oxidation number is also 0. Now, if I look over at the product side, now strontium oxide is not an element. that's a compound. So what I'm going to have to do is refer back to my rules of oxidation numbers and see if I can figure out the oxidation numbers for this particular compound. Now, the easiest thing to do here is consider the oxygen first. We said that oxygen in every compound but peroxides should have an oxidation number of -2. And strontium, we may not be 100% sure of, but if you recall, neutral compounds, their oxidation numbers should sum up to 0. So if I add up the oxidation numbers, right, so if I sum the oxidation numbers for the strontium oxide, then the sum should be 0. And the only oxidation number that I have available to me for strontium oxide so far is -2. And I'm going to add strontium's oxidation number to it. So that means that the oxidation number for strontium should be +2. Because if I add +2 and -2 together, then I will get 0. Note that the stoichiometric coefficient does not affect the oxidation number. The other point is that I want to make sure you guys understand that when we report oxidation numbers, we report them per individual atom. All right, we don't lump them all together. So what I mean by that is, take the second reaction here. Okay, here in methane, I have carbon and hydrogen bonded together. Hydrogen is bonded to the nonmetal carbon, so that means that its oxidation number is +1. Now note that there are 4 hydrogens, but I don't report the oxidation number of hydrogen as +4. I would report it as +1 because each individual hydrogen atom has an oxidation number of +1. All right? However, I do have to take into account that there are 4 hydrogens so that I understand that when I add the oxidation numbers for the 4 hydrogens, so far I have +4 positive oxidation numbers built up, and these oxidation numbers have to add up to 0. That means that the oxidation number for carbon has to be -4. Here we have elemental oxygen again. So the oxidation number for oxygen is 0. In carbon dioxide, the oxidation number for oxygen is -2 because carbon dioxide is not a peroxide. -2 times 2 is -4. If that's going to sum up to 0 because carbon dioxide is a neutral compound, then that means that carbon should have an oxidation number of +4. The oxygen in water also has an oxidation number of -2. And the hydrogen, because it's bonded to an oxygen, and oxygen is a nonmetal, then the oxidation number for hydrogen should be +1. +1 times 2 hydrogens should give me +2 positive oxidation numbers. Added to -2 oxidation numbers, that sums up to 0, as it should, for water as a neutral compound. Now, let's actually go back and take a look at what's going on in each of these reactions. Notice that for the strontium, its oxidation number is changing from 0 to +2. It's getting more positive. And the reason it's getting more positive, it's because it's losing 2 electrons. And if you recall, oxidation is the loss of electrons. If we take a look at the oxygen, oxygen is going from 0 to -2. It's gaining negative charge, or gaining 2 electrons. So that means that the oxygen is being reduced. All right, let's do the same here for the bottom reaction. If you notice, carbon is going from an oxidation number of -4 to +4. It's getting more positive because it's losing 8 electrons. So the loss of electrons is oxidation. All right, if we take a look at the oxygen, oxygen's going from an oxidation number of 0 to -2. So it's getting more negative because it's gaining 2 electrons, and that's reduction. So do the follow-up assignment. Tomorrow we'll take some additional examples of trying to sort of deconstruct oxidation-reduction reactions, and we'll take it from there. I'll see you guys in class tomorrow.